Okay, so today we are going to be moving on to Chapter 4, Relations and Functions. So 4.1 is exactly that, relations and functions. An algebraic expression like 3x plus 1 defines a set of ordered pairs, x, y. For every x we input into the expression, we get 3x plus 1 as output. So every point is x, comma, 3x plus 1. So the 3x plus 1 is depending on what x is. In set builder notation, you write the little squiggly, braces, and then x comma y colon y equals 3x plus 1. And that colon is read such that. A relation is a set of ordered pairs. Okay, so if you look at the table a little bit farther down, you've got a set of ordered pairs. That's a relation. A function is a special relation. In which no two ordered pairs have the same first element, or x. X's will go. So basically for a function, no x coordinates can repeat. Okay? So no x coordinates can repeat. So the ordered pairs for y equals 3x plus 1, if you look to the right, depend on the first element x. X can be chosen and has no restriction. In other words, we can substitute into x any number we want. Pi, 0, 2.7, any number, radical 3. There's no restriction. There's nothing that's going to make this equation undefined. Therefore, we say the domain of the function is all real numbers. So, to define that, the domain of a function is the set of all x values that can be chosen as input. So, for example, what can we use or choose for x so the result is a real number in each problem below? This is another way to ask, what is the domain? So you have some restricted domains. These are subsets of the set of reals, partial parts of the reals. You can have no negatives under the radical, no zeros in the denominator. Okay, so watch for x under the radical and x in the denominator or both. All right, so with a fraction, to find out my restricted domain, I set the denominator equal to 0. For radicals, I set the radicand to greater than or equal to 0. And for radicals in the denominator, I set the radicand to greater than 0. Okay, so some things to help you when you're doing these. So I'm looking for what is the domain on number 1. There's no negative under a radical. There's no fraction. So the domain is all reals. So I'm putting a D. Okay, so it's just all reals. So another way to put that, could be x such that x equals all reals, because you're talking about the x coordinates. All right, now parabola, y equals x squared, number 2. It's not a fraction. There's no radical. So I don't have a restricted domain. I can substitute any number I want in for x. So again, the domain is all reals. X such that x equals all reals. Number 3, now we have a radical. What is our domain? Our domain with this radical, if you look here, with radicals, I cannot have negatives under there. So set the radicand, which is the x minus 4, greater than or equal to 0. Because that means that will give me the x values such that they will be greater than or equal to 0, positive. So x is greater than or equal to 4. That is my domain. So my domain is x must be greater than or equal to 4. On number 4, I have a fraction. I cannot have every number substituted in for x. So I cannot say the domain is all real numbers. I can say it's all real numbers except 5, because that's going to make the denominator undefined if I let x be 5. So in my fraction part, I set the denominator equal to 0, which is what I did up here. I mentioned that. So then x is equal to 5. Cannot be part of the domain. You can plug in any number you want in for x except 5. So you say that your domain is x not equal to 5. You could also say that your domain is all reals except 5. Okay, and then on number 5, now we have a radical in the denominator. So for that one, I set the radicand greater than 0 because I cannot have it equal to 0 on the denominator, and I cannot have a negative under the radical. So I'm going to say I want what's under the radical to be greater than 0. I don't want it to be equal to 0, because then that would mean it would be undefined. And I don't want it to be negative, so greater than 0. So x must be greater than 5. So if you plug in 5.1 for x, that gives you a positive radical, not 0. I'm trying to look for values that I can plug in for x so that the result is a real number. And x is greater than 5 is my domain. So for this one, we'd say the domain is x is greater than 5. Okay, now the range of a function is the set of all y values that are output. So is the set of all y values that are output. So identify the range for each example above. So on number 1, every x value that you plug in yields a y value. So the range is all real numbers. So I use R. Range is all reals or y such that y equals all reals, because I'm looking at the y coordinates. Number 2, I need to have a graph, okay, to figure out this range. So y equals x squared. If we take and we open up our calculator, give me a second to do that. And we go to y1 and we enter in x squared, and I go to zoom 6. You can see that it's a parabola that looks like that. So I'm going to draw the sketch like that. The minimum point is clearly 0, 0. Okay, so my little sketch here gives me this kind of a figure. All right, so the domain was all reals because it's all possible x values. But I'm never going to get any y coordinates that are negative, and you can verify that algebraically by looking at the equation. Y equals x squared. Everything squared comes out positive. And look at the graph. The graph is never going below the x-axis. So we say that the range is y is greater than or equal to 0. And if you look back at the calculator, and if you look in the table, so second graph, and you look at all the y coordinates, there's not one of the y coordinates that's negative. The y's are never going to be negative. So y is greater than or equal to 0. That's our range. For number 3, we have y equals the square root of x minus 4. So again, I'm going to go back and go to y equals, get a little sketch. So that's second square root of x minus 4. So x minus 4. And I'm just going to hit graph this time because I already hit zoom 6. And so it looks like it's coming off here at the coordinate 4, 0. So when I draw the sketch, I'm going to put this in a different color. It looks like it's going like that. So again, notice that it's going off to the right. That's why the x was greater than or equal to 4. So for the domain, you look left and right. For the range in the graph, you look up and down. Notice that again, there are no y coordinates that are going to be less than 0. So again, we would say the range is y is greater than or equal to 0. If we go back to the calculator and we look at the y coordinates in our list there, okay, you can't have negatives under radicals. So all of a sudden, once you get above 4 here, you start to see y coordinates. And the smallest y coordinate is going to be 0. So all your y coordinates are greater than or equal to 0. That is your range. Number 4 is y equals 3 over x minus 5. So you're not going to be able to have x equal to 5. So the graph of that is going to be an interesting looking graph. So go back to y equals and clear that out and enter in 3 divided by parentheses x minus 5. Okay, so what it's going to do is give you kind of like a hole at 5 because x cannot be 5. So it's going to deviate away from that. So the graph of that one, 1, 2, 3, 4, 5, went, oh, I just forgot what it looked like for a quick second here. Okay, got it. So it went like this, and it went like this. There's a thing called an asymptote, which is where it's undefined. We kind of sometimes put in with a dotted line. That's where it's undefined. And so if x were allowed to be 5 and there'd be a 0 on the bottom, then y would turn out to be 0. So notice how it kind of, the graph kind of seems to hover but not go over the x-axis. So this one we say that the range is y does not equal 0. If x were 5, then that denominator would be 0 and y would be 0, but y can't be 0 because x can't be 5. That's a little bit more complicated. We'll do some more. For number 5, for that one, if we take a look at that graph, clear that one out, we have 3 divided by the square root, 3 divided by the square root of x minus 5. And when I graph that, now it doesn't show me the other piece because we cannot have, our x coordinates have to be greater than 5. Okay? So for this graph, I'm going to draw 1, 2, 3, 4, 5. It's not going over 5, and it's really not seeming to touch that x-axis either. It's like, again, there's a, there's like a dotted line here that it's not crossing, and then there's one on the x-axis it's not crossing. So in this case, we say the range is y is greater than 0. Okay, because we do have values for y, but they are greater than 0. Okay, so look up and down. The graph itself does not have any values equal to 0 or less. And again, if you go back to the table, you can see that at 6 you get 3. At 5.1 you would also get a number. And we can check on that. So we can go to second, right there, and have the table. I'm just going to go to second trace instead and do value. And I can say x equals 5.1, and it will tell me what's going on at y. And it's saying 9 point something. Okay, so if I said 5.001 for x, it would be even larger. So the y value is increasing. So y is greater than 0. Okay, let's go to the next page. All right. Another definition for function. A function from set A to set B is a set of ordered pairs such that every x in A, that would mean in set A, is paired with exactly one y in B. Okay, so that's like a more formal definition. So for every x, there's only one y, no repeating x coordinates. Function from set A to set B is onto, that's another word that sometimes comes up, if the range of the function is equal to set B. The next page also gives you an example. Basically what you're looking for here, so basically looking to see if all values have been used in set B. Okay, so we'll come across these here. So a constant function is y equals a. So for example, y equals 3. Graph, what is the domain? Look left and right. There's arrows both directions. There's every single x-coordinate you could think of would be on this line. So we say the domain is all reals. The range, though, look up and down at the graph. The only y-coordinate that is on this graph is y equals 3. So we say y equals 3. Is it on to? The range for the horizontal lines change, so it's not going to always remain the same. This is no. You would not have all the values being used in set B, which would be, all reals. There's only certain values that are being used at a time, and so it is not onto. The example B, a linear function. You should remember y equals mx plus b. Graphed y equals 1/2 x plus 1 for you. Domain, there's any possible number you want to plug in for x, you can plug in, so we say the domain is all reals. The range, any possible number is going to come out once you enter a value in for x, so we say the range is all reals. Is it onto? Yes, because every value from the range will be used. That's set B. Set A is your domain, set B is your range, and what we use to determine if it's onto or not. The quadratic function, y equals ax squared plus bx plus c, if I factor that real quick, x minus 1, x minus 3, my zeros are going to be at 1 and at 3. If I find my minimum, that's x equals negative b over 2a. That turns out to be negative b, which is 4 over 2 times 1. So that's 2. And then if I plug 2 back into the original equation to find out what y is for that minimum coordinate, I would get 2 squared is 4 minus 8 plus 3, which is negative 1, negative 4 plus 3. So my minimum's at 2, negative 1. So here's 2, negative 1. It goes through 3 and 1, which is why I found those zeros at 3 and 1. Okay, so the domain, there was nothing that I couldn't put in for x, so the domain is all reals. The range, however, if you look, there's not going to be any y-coordinate below this minimum point of 2, negative 1. So the range, all the y-coordinates are going to be greater than or equal to the y-coordinate of the minimum. Is it onto? No, because the range for the quadratic functions change. They're not going to be all the same. The absolute value function is the next one. For this one, we already have the graph. This is 1 and negative 3. The domain is all reals because there's no limit to what we can plug in for x. We can plug any number we want in and we will not get undefined. The range, you need to know that minimum point. So that minimum point is negative 1, negative 2. So I'm looking for the fact that all the y-coordinates would be greater than that minimum y-coordinate. So y would be greater than or equal to negative 2. It is not onto for the same reason that parabolas are not onto. The ranges will change for absolute value functions based off of the original, an absolute value function. The square root function, y equals the square root of x, or y equals square root of ax plus b, basically kind of starts where it starts, and then it trails off. That's our sketch. So the domain, you can't have negatives under the radical, so your domain must be x is greater than or equal to 0. And your range is y is greater than or equal to 0. Okay, because you can see your y coordinates are going to be going up, your x coordinates are going to the right. There's an arrow, so it's going to keep going on. Every y coordinate from this original graph will be used. So onto is yes. I did not mean to write no. That absolute value graph onto is yes. Okay, the next one, y equals the square root of x plus 3, is going to start back here at -3 and take on that same kind of pattern as the first one. The domain is going to be x is greater than or equal to -3, and the range is y is greater than or equal to 0. And this is also onto every possible y coordinate from an absolute or from a square root graph is going to be used. So that is onto. Next page. Almost done. A relation is a function if no two pairs of the relation have the same first element. The x value cannot repeat. Okay, so a couple of examples. Are they functions or not? The first one, we're only looking at the x coordinates. Do they repeat? No, they do not. Therefore, yes, this is a function. Number 2, we got a problem. The 2's repeat, not a function. Number 3, 1, 2, 3, all different. Okay, you can also tell if something's a function on a graph. A vertical line drawn anywhere through the graph will intersect a function at only one point. This is called the vertical line test, or VLT. Anybody hungry? BLT, VLT? Which of these is a function? So some examples here. So if you take a parabola, if I take and draw a vertical line, it hits it in only one spot. No matter where I draw that vertical line, it only hits it in one spot. Yes, that's a function. But if I take that parabola and I put it on its side, now when I draw a vertical line, it's hitting it in two spots. So maybe that coordinate is 2 comma something and this coordinate's 2 comma something. Doesn't matter what the y coordinate is. You've got repeating x's. No. Number 3, interesting looking graph. If I go like this and I go like that, you see they have this coordinate 0, remember, and this coordinate 0. So they have those in common. So again, no. But if I take that same graph and I do a closed circle and an open circle, then this open circle is not part of the graph. Only the top closed circle is. So this does pass the vertical line test, yes. If you take just some sort of crazy graph like that, that is not going to pass that vertical line test. If you take a line, that passes the vertical line test. If you take a vertical line, no, that does not pass. Every single one of those x coordinates repeat. If you take an absolute value graph, yes. And a square root graph, yes. And one more, if I just add on here a number 10 and put a circle in there, no, that is not going to pass the vertical line test. All right, so that should bring us to the end.